Okay, fundamental idea is the idea of how systems of simultaneous linear equations relate to matrices. So here's a matrix product. Okay, so simple matrix product. We can write this product out. If I multiply here on the left side, 2 times x is 2x, 3 times y is 3y, negative 1 times z is negative z. Negative 5 times x is negative 5x, 2 times y is 2y, 4 times z is 4z. Again, multiplying the first row by the only column we have here, and then multiplying the second row by that column, we get this. Now this is still a matrix of 2 rows, but of course the matrix has rows that represent different combinations of the variables x, y, and z. Okay, and then on the right hand side we still have -5, -9. Well, if this matrix is going to equal this matrix, then whatever we have in this row has to be equal to whatever we have in this row. Otherwise, matrices are not going to be equal. If the first row is not equal to the first row, the matrices are not equal. And the second row has to equal what's in the second row. So now we have 2 simultaneous equations. This has to equal this, so we can write out 2x plus 3y minus z equals 5, and negative 5x plus 2y plus 4z equals negative 9. Now we could proceed to solve this equation by elimination. And I am assuming that everybody knows how to solve simultaneous linear equations by elimination. One comment. We don't use substitution to solve simultaneous equations. In linear algebra. It's unnecessary because the equations are linear. Now if I had a square on the x or a square root on the z, then we'd be in a different ballpark and we would be stuck with substitution. But in linear algebra, everything is linear. All the powers are 1, and we don't need it, and we don't use it. Now, there's exceptions to every rule. I can't think of an exception to this, but there's probably one that I'm not thinking of. And when you get into use of, well, into differential equations and so forth, we encounter a lot of situations that are nonlinear where we have to use substitution. And of course, in calculus and pre-calculus, there are a lot of cases where you have curves defined by nonlinear functions. And if you want to find intersections, you've got to use substitution. We don't have to do any of that in linear algebra. Linear algebra has its own areas of difficulty, but that's not one of them. Okay? Okay, well, we see that then any matrix equation multiplying a matrix by a column vector to obtain another column vector is equivalent to a system of linear equations. So I can say generally the equation ax equals b, and notice I have an arrow over the x and an arrow over the b. I'll say where x and b are column matrices. In other words, matrices that consist each of one column only. Any such product is equivalent to a system of simultaneous linear equations, and vice versa. Any system of simultaneous linear equations can be written in this form. So, the other statement can be written, any system of simultaneous linear equations can be written in the form ax equals b, where the arrow over the x and the arrow over the b indicate that these are column vectors. Column matrices, but we're going to call those vectors. So, let's see if we've got room, yeah. Column matrix can also be called a column vector, and can represent a vector in a vector space, but that's a topic that we'll get to in just a little while. Okay, so big deal. System of simultaneous equations and matrices are basically equivalent. If you've got a matrix product with column vectors, you can write it as a system. If you've got a system of simultaneous linear equations, you can write it as a matrix product.